Technology is reshaping the world faster than ever, and 5G Core Networks helps you make sense of it. We will focus on what it says about network and service. Stay with me, the best part is near the end. Chapter 1, Introduction. 5G, a new era of connectivity, a step change, a new context for operators, the road to 5G network deployments, 3GPP Release 15 and 16 core requirements, new service grade structure of this book. Chapter 2, Architecture Overview. Introduction to Perspectives on 5G Core Service-Based Architecture, SBA. The core of the core, connecting the core network to mobile devices and radio networks, mobility and data connectivity, policy control and charging, 5GC interworking with EPC voice services, messaging services, exposure of network information, device positioning services, network analytics, public warning system, support for devices connected over non-3GPP access networks, network slicing, roaming, storage of data, 5G radio networks. Chapter 3, Session Management. PDU Session Concepts. PDU Session Types. User Plane Handling Mechanisms to provide efficient user plane connectivity, edge computing, session authentication and authorization, local area data network. Chapter 4, Policy Control and Charging. Introduction. Overview of policy and charging control, access and mobility related policy control, UE policy control, management of packet flow descriptions, network status analytics, negotiation for future background data transfer, session management related policy and charging control, additional session related policy control features, charging. Chapter 5, Dual Connectivity. Introduction. Multi-RAT dual connectivity, overall architecture, MRDC, UE and RAN perspective, MRDC, subscription, QoS flows and ERABS, MRDC bearers, managing secondary RAN node, handling for mobility and session management, security reporting, user data volume traversing via SN. Chapter 6, Protocols. Introduction. 5G non-access stratum, 5G NAS, NG Application Protocol, NGAP, Hypertext Transfer Protocol, HTTP, Transport Layer Security, TLS, Packet Forwarding Control Protocol, PFCP, GPRS Tunneling Protocol for the User Plane, GTPU, Extensible Authentication Protocol, EAP, IP Security, IPsec, Stream Control Transmission Protocol, SCTP, Generic Routing Encapsulation, GRE. Chapter 7, Selected Call Flows. Introduction. Registration and deregistration service request, UE configuration update, PDU session establishment, Inter-NGRAN handover, EPS interworking with N26 EPS fallback procedures for untrusted non-3GPP access. Chapter 8, Network and Services. Introduction. This chapter provides an overview of how the 5G standards started and some of the key background areas that readers need to understand the specifications. The final section of the chapter outlines the structure of the book. 5G, 5G Core, 5G Networks, Introduction. Chapter summaries. 5G, a new era of connectivity. The telecommunications industry has embarked on a dramatic transition, and one that, if successful, will see it redefine its role in industry and society. 5G, while often portrayed as a tool for higher speeds or critical to the development of the so-called industry, represents a foundational shift for wireless communications, one that places it directly at the center of a truly digital economy. This overhaul of communications is therefore unlike any that have gone before. It is not the same as the move from 2G to 3G or 3G to 4G. It is a step change that the industry may not see again for quite some time. The 5G architecture itself consists of two parts: the new radio network, NGRAN, supporting the new radio, NR, and the 5G core network, 5GC. Both have changed considerably compared to previous generations of technology. This book focuses on 5GC, providing short forays into NR where it aids understanding of the interactions towards the core network. A detailed description of NR is, however, beyond the scope of this book, and interested readers are directed to Dahlman et al. A step change. The first broad-scale adoption of mobile technology started with GSM, 2G, released in 1991, which focused on calls and text messaging. WCDMA, 3G, released in 1999, gave consumers the ability to browse the internet and use feature phones. It was not until the introduction of LTE, 4G, in 2008, however, that we saw the broad adoption of mobile broadband, MBB, and the uptake of video and data traffic on the all-IP network, including the development of apps on smartphones. Each generation saw a large increase in bandwidth and speeds provided, with end-user consumers as the core focus. 5G is unlike the previous generation of networks. It represents a shift from operators having end users as customers to over time having industries as their main customers. This represents not just a technology shift, but a business model shift unlike any previously as well. New players may very well enter the market because of the disruptive capabilities of 5G. 5G is a more ambitious approach to network architectures, not only incorporating requirements from the telecommunications industry but other industries, and at the same time including cloud-native and web-scale technologies such as HTTP. It is quite simply a new approach to developing architecture and delivering services on a global scale. A new context for operators broken up into building blocks covering access, transport, cloud, network applications, and management, including orchestration and automation. 5G systems aim to provide a higher level of abstraction designed to simplify network management and operations. In addition, new services will need to be rapidly implemented on the network as new business models emerge that demand operators move to programmable, software-based networks that deliver services on demand and in an as-a-service manner. Throughout this book, we illustrate where the technology itself overlaps with some of these new business models, providing a unique insight into how some of those decisions have been made. In addition, where previously human customers were making requests of the networks, with 5G there is an increased level of non-human, machine and software, requests. That means the entire way services are developed and delivered needs to change. The road to 5G network deployments. The initial work on defining the requirements and vision on 5G networks was carried out in ITUR in 2012. ITU formally refers to this as IMD 2020. A good reference is Dahlman et al. This was followed by multiple more detailed studies in ITUR itself, as well as in industry fora and research projects around the world. The initial work to develop the 5G specifications to meet the ITUR IMD 2020 requirements was done in 2014, picking up speed in 2015 and 2016. Trials of 5G systems have been in place in several countries, with commercial rollouts planned for most markets around 2020. Outlining the core network evolution in an easy-to-use and accessible manner so that engineers and other interested parties can understand the changes brought about by 5G is therefore the core reason for us writing this book. Several early commercial 5G systems became available already from late 2018 and early 2019. Some initial 5G network deployments include Verizon and AT&T have both launched USA's first 5G services during 2018 and 2019. Telstra has rolled out multiple 5G areas across Australia during 2018 and 2019. Services targeting enterprise use cases launched by all three Korean operators by the end of 2018. Early eMBB services were launched in Korea, the Switzerland, and the U. In the first half of 2019, 3GPP Release 15 and 16 5G Core is described in a set of specifications developed by the third Generation Partnership Project, 3GPP, and captured in Release 15, REL 15, and subsequent releases. REL 15 was the first full set of 5G standards and was released in several steps between June 2018 and early 2019. REL 16 is planned to be released early 2020 and planning of work has commenced on Release 17 with an aim to have specifications ready in 2021 or 2022. REL 15 contained E, Architecture for Non-Standalone, NSA, I, New Radio, and R, used with the LTE and EPC Infrastructure Core Network Architecture for Standalone, SA, I, NR is connected to the 5G Core Network, 5GC, 5GC using a service-based architecture, SBA, support of virtualized deployment network functionalities to provide registration, deregistration, authorization, mobility, and security data communication with IP, Ethernet and unstructured data support of concurrent local and central access to a data network support for edge computing network slicing unified access control converged architecture to support non-3GPP access policy framework and QoS support network capability exposure multi-operator core network, I, sharing same NGRAM by multiple core network support of specific services such as SMS, IMS, Location Services for Emergency Services Public Warning System, PWS, Multimedia Priority Services, MPS, Mission Critical Services, MCS, PS Data Off Interworking. Between the 5GS and 4G REL 16 is set to contain several additions, many specifically aimed at different industry verticals. Chapter 9, V2X. Access Traffic Steering, Switch and Splitting Support in the 5G System Architecture, ATSSS, Cellular IoT Support and Evolution for the 5G System, 5G_CIoT, Enablers for Network Automation for 5G, ANA, Enhancing Topology of SMF and UPF in 5G Networks, ETSN, Enhancement to the 5GC Location Services, 5G_ELCS, Enhanced IMS to 5GC Integration, EIMS 5G_SBA, 5GS Enhanced Support of Vertical and LAN Services 5G LAN Aspects 5GS Enhanced Support of Vertical and LAN Services TSN Aspects 5GS Enhanced Support of Vertical and LAN Services Non-Public Network Aspects System Enhancements for Provision of Access to Restricted Local Operator Services by Unauthenticated UEs, PARLOs, not for 5G Enhancements to the Service-Based 5G System Architecture, 5G_ESBA, Enhancement of URLLC Supporting in 5GC, 5G_URLLC. User Data Interworking and Coexistence, UDICOM, Optimizations on UE Radio Capability Signaling, RACS, Wireline Support, 5WWC, Core Requirements. The 5GC has been designed to implicitly and explicitly support several architectural principles. Support for a service-based architecture for modularized network services, consistent user experience between 3GPP and non-3GPP access networks, harmonization of identity, authentication, QoS, policy, and charging paradigms, adaptation to cloud-native and web-scale technologies, edge computing and nomadic/fixed access. Bring computing power closer to the point where sensor data from remote, wireless devices would be collected, eliminating the latency incurred by public cloud-based applications, improved quality of service, and extend that quality over a broader geographic area. Machine-to-machine communication services that could bring low-latency connectivity to devices such as self-driving cars and machine assembly robots. The architectural impacts of these are described more fully in Chapter 3. New service grades 5G allows for 3 service grades that may be tuned to the special requirements of their customers' business models. Enhanced Mobile Broadband, EMBB, aims to service more densely populated metropolitan centers with downlink speeds approaching 1 gigabit per second, gigabits per second, indoors, and 300 megabits per second, megabits per second, outdoors. Massive Machine Type Communications, MMTC, enables machine-to-machine, M2M, and Internet of Things, IoT, applications that a new wave of wireless customers may come to expect from their network, without imposing burdens on the other classes of service. Ultra-reliable and low-latency communications, URLLC, would address critical needs communications where bandwidth is not quite as important as speed, specifically, an end-to-end latency of 1 millisecond or less. Structure of this book. This book is roughly divided into 4 separate parts. Part 1, Introduction, Architecture, and Scope of Book. Chapters 2-4 provide an introductory overview and scope of the book. This includes the key technologies used within 5GC and a high-level architectural introduction. Forms the basis of understanding for the rest of the book. Meanwhile, illustrates EPC for 5G. More details of this is beyond the scope of this book, but interested readers are referred to 3GPPTS. Part 2, Core Concepts of 5GC. Chapters 5-12, meanwhile provide a comprehensive overview of all the core concepts of 5GC that readers require to understand the entirety of the system. This includes modeling, session management, mobility, security, QoS, charging, network slicing, and dual connectivity solutions. These concepts form a fundamental base for the remaining chapters. Part 3, 5GC Nuts and Bolts. Chapters 13-15 provide the in-depth knowledge required for all practitioners in the 5GC space, going into detail of how the core concepts in Part 2 fit together and work as a unified whole to deliver the 5G core network. Readers are presented with deep dive into network functions, reference points, protocols, and call flows. After reading Part 3, readers will be ready to work with 5GC. Part 4, Release 16 and beyond. Chapters 16 and 17 conclude the book with a description of architecture extensions in Release 16 and some overview of the support for vertical industries. The book concludes with a future vision for the development of 5GC going forward. References 3GPPTS, 3GPP Technical Specification, 3GPPTS, 3GPP Technical Specification, General Packet Radio Service, GPRS, Enhancements for Evolved Universal Terrestrial Radio Access Network, EUTRAN, Access. Dahlman, et al. 5GNR, the Next Generation Wireless Access Technology. Elsevier, 2018. Chapter 10, Network and Mobile. Drivers for 5G. This chapter outlines the overall drivers for the development of the 5G core and illustrates some of the key use cases that drove the 5G standards. The drive for fixed wireless. Critical new technologies such as virtualization, cloud-native, containers, microservices, and automation are also covered, illustrating how all of these combined with 5GNR provide for a dramatically upgraded network that can deliver services across enterprises and industries as well as to end-user consumers. 5G, 5G core, 5G networks, drivers, use cases. Introduction. The requirements on mobile and other types of communications networks have been growing significantly over the past decade. From humble beginnings just providing phone calls and text messages, these networks are now expected to form the underlying infrastructure for a truly digital economy, enabling new means of operation as the world transitions from 20th century operating models into ones that are designed for the challenges of the 21st. The drivers for 5G are far more, therefore, than merely the drive for a new core network but rather the result of intersecting requirements and demands, namely, 1. Business case demands from a broader set of economic actors, including industrial companies driving new use cases. 2. New technologies for delivering core network components, creating expectations of more efficient and flexible operations. And 3. Shifts in how business, society, and environmental needs are balanced to deliver services in a new way. New use cases. Previous versions of mobile technologies illustrated the potential of these technologies to deliver innovative, previously unthought of services to a global subscriber base. These have driven ideas and expectations about what the next generation of mobile technologies could bring, creating a broad-ranging set of market expectations on what value 5G technologies will bring to different industries and areas of society. The possibilities for both significant cost savings and new revenue enablers has therefore created a large interest in 5G across multiple industries, not only among traditional mobile service providers and users. For services that already are offered using 4G or older technologies, such as mobile broadband services, 5G is providing both an enhanced user experience and a more cost-efficient solution. The enhanced user experience is mainly experienced as overall higher data rates, not so much about higher peak data rates, but more about providing an increased average data rate across the network. Users of mobile broadband services will therefore experience a higher quality of service. Also related to the consumer segment, there are expectations that the low latency of 5G radio access would nicely suit time-sensitive services such as mobile gaming. While the full business case to design infrastructure to cater for mobile gaming or other low-latency sensitive services remains to be developed, the types of possibility that 5G enables are one of the core drivers for its implementation. From the service provider side, a major challenge is the ever-increasing data volumes in the networks, and 5G comes with the promises of being able to offer capacity expansion more cost-efficiently than if the expansion is done with existing 4G per LTE technologies. On the network operations side, meanwhile, expectations are that the new 5G network architecture would give additional benefits in terms of increased support for automation of various operational processes. This could be, for example, network capacity scaling, software upgrades, automatic testing, and usage of analytics to optimize network performance. Also, the possibility to deploy new software and new services easier and at lower initial cost is imperative for many operators. While 3GPP is actively working on enablers for automation and for cloud deployment, it must also be acknowledged that some of the possible gains in this area are coming from implementation decisions by the companies designing the infrastructure software. Not everything is subject to standardization or is even possible to standardize. 5G is not just about mobile networks either. Fixed wireless access solutions are receiving an increased interest with the emergence of 5G solutions. The market for connecting residential homes and enterprises with high-capacity broadband solutions is growing significantly globally, and with 5G technologies there is a new option on the table for service providers that provides high speeds without the costs of implementing fixed infrastructure. It can be assumed that for some geographical areas, delivering broadband services over the air using 5G access technologies is among the best and most cost-efficient solutions. This adds to the interest for 5G among some service providers. One of the initial key drivers for the new 5G core architecture and the associated principles for access technology independence was converging the operations for various types of technologies. This would mean that a service provider that offers both mobile and fixed services to its customers could in the future utilize a single operational team, a uniform set of infrastructure solutions, and identical operational processes across the different service offerings. If this happens, this would mean that the concept of fixed mobile convergence would finally be realized, a wish since long from large service providers with significant fixed service business and extensive cost for their operations across mobile and fixed services. When looking beyond the enhancement of today's services from a user experience, capacity optimization, or operational efficiency perspective, a whole new area of use cases are creating drivers for 5G technologies. This is coming from the collective set of use cases that can be applied to industry digitalization, meaning that the special characteristics of 5G technologies in terms of very low latency, very high data capacity, and very high reliability can be utilized to optimize existing industrial processes or solutions, or even realize completely new ones. Many new business opportunities can be envisioned here and has been outlined by many, for example, Ericsson and Arthur D. Little, A. Little, 2017. The wide range of industry sectors that are being targeted and explored include, for example, industrial manufacturing, public safety, energy production and distribution, automotive and transport, and healthcare. This could, for example, mean utilizing the massive capacity scalability targeted with 5G to support data collection from large numbers of sensors and devices in order to perform advanced data analytics on different IoT and CPS solutions. It could also mean utilizing the very high reliability or low latency of 5G to design more flexible and robust industry communication solutions, for example for real-time control of robots in a variety of different industrial manufacturing and other systems. Another potential use case area is to enhance industrial processes using AR/VR technologies to support operational personnel in troubleshooting, general maintenance, or to safely perform operations in dangerous environments. While it can be assumed that all use cases will not be commercially or technically viable, the sheer range of use cases being explored will mean that 5G can be expected to play a significant role in general industry digitalization for the years to come. This is one of the main drivers for why the global community across multiple industry sectors is increasingly looking at 5G as a key component for their future business operations. Many new technologies have driven the development of 5G. In this section we very briefly discuss the main ones. 1. Virtualization. 2. Cloud native. 3. Containers. 4. Microservices. And 5. Automation. Virtualization. Traditionally, mobile core network element functional designs are distributed applications which scale horizontally and run on dedicated hardware such as processor blades and a chassis. The network element architecture is distributed internally onto specific types of blades that perform specific tasks. For example, blades that execute software that is responsible for overall management of the network element versus blades that perform the actual work of managing mobile core subscribers. Scale is achieved primarily by internal horizontal scaling of working blades. The first major step of virtualization was to migrate those application-specific blades to virtualized resources such as virtual machines, VMs, and later containers. ETSI-NFV, Network Function Virtualization, and OPNFV was created to facilitate and drive virtualization of the telecoms networks by harmonizing the approach across operators. The network element could then be realized as an application that is distributed among several virtual hosts. Because the application was no longer constrained by the resources and capacity of a physical chassis, this step allows much greater flexibility of deployment and for harmonization of the installed hardware. For example, the operator can deploy much larger, or even much smaller, instances of the network element. This first step was also mainly for proving that a virtualized host environment could scale appropriately to meet the subscriber and capacity demands of today's mobile core. However, most applications in this phase are like a two-tier application design wherein the second, logic, tier the application itself was tightly coupled to state storage it required. The storage designed to maintain state was ported from physical systems where individual blades had their own memories. The next step in the mobile core architecture evolution is to a cloud-native design to take advantage of the flexibility offered in using cloud technology and capabilities. In this step, the mobile core network element design that was tightly integrated together in predefined units and ratios is now decoupled both logically and physically to provide greater flexibility and independent scalability. For example, this step sees further separation of control plane and user plane of a network function. Also, in this cloud evolution, mobile core functions begin to implement the network architecture of web applications. Cloud-native architectures have gained a lot of interest over the past years, and service operators attempt to emulate the efficiencies captured by so-called hyperscalers, Facebook, Google, Amazon, has led to a much heightened interest in this area. Simply put, the architectures and technologies, service-based interfaces, microservices, containers, etc., used in web-scale applications bring benefits to networking infrastructure in elasticity, robustness, and deployment flexibility. Cloud-native applications and infrastructure should not be viewed as another level of complexity on top of a cloud transformation that still is not fully up and running. Rather, it should be viewed as a natural evolution of the cloud transformation that is already in progress in the telecom industry today. A cloud-native strategy therefore allows service providers to accelerate both the development and deployment of new services by enabling practices such as DevOps, while the ability to rapidly scale up or scale down services allows for resource utilization to be optimized in real time, in response to traffic spikes and one-time events. There are several cloud-native design principles that hold for all installations, including infrastructure agnostic. Cloud-native applications are independent and agnostic of any underlying infrastructure and resources. Software decomposition and life cycle management. Software is decomposed into smaller, more manageable pieces, utilizing microservice architectures. Each piece can be individually deployed, scaled, and upgraded using a COS, container as a service, environment. Resiliency. In legacy applications, the MTBF, mean time between failures, of hardware has been the base metric for resiliency. In the cloud, we instead rely on distribution and independence of software components that utilize auto-scaling and healing. This means that failures within an application should cause only temporary capacity loss and never escalate to a full restart and loss of service. State-optimized design. How we manage state depends on the type of state/data and the context of the state. Therefore, there is no one-size-fits-all way of handling state and data, but there should be a balance between performance, resiliency, and flexibility. Orchestration and automation. A huge benefit of cloud-native applications is increased automation through, for example, a Kubernetes-based COS layer. A COS enables auto-scaling of microservices, auto-healing of failing containers, and software upgrades including canary testing, small-scale testing, before larger deployments. Containers virtualization has revolutionized IT infrastructure and enabled tech vendors to offer diverse IT-based services to consumers. From a simplistic perspective, system-level virtualization allows instances of an operating system, OS, to run simultaneously on a single server on top of something called a hypervisor. A hypervisor is a piece of computer software that creates and runs virtual machines. System-level virtualization allows multiple instances of OS on a single server on top of a hypervisor. Containers, on the other hand, are isolated from each other and share OS kernels among all containers. Containers are widely used in sectors where there is a need to optimize hardware resources to run multiple applications, and to improve flexibility and productivity. In addition, the ecosystems and tooling for container-based environment, Kubernetes, are rapidly expanding. Containers are especially useful for telecommunications applications where low latency, resilience, and portability are key requirements in edge computing environments. For implementing short-lived services, for highly agile application deployments. In machine learning or artificial intelligence, when it is useful to split a problem up into a small set of tasks, it is expected therefore that containers will assist to some extent with automation. Microservices are an architectural and organizational approach to software development where, rather than be developed in a monolithic fashion, software is composed of small independent services that communicate over well-defined APIs. It is often considered a variant of the service-oriented architecture approach. The overall aim with microservices architectures is to make applications easier to scale and faster to develop, enabling innovation and accelerating time to market for new features. They also, however, come with some increased complexity, including management, orchestration, and create new data management methods. Microservice disaggregation has several benefits. Microservice instances have a much smaller scope of functionality and therefore changes can be developed more quickly. An individual feature is expected to apply to a small set of microservices rather than to the entire packet and 5GC function. Microservice instances can be added/removed on demand to increase/decrease the scalability of their functions. Microservices can have independent software upgrade cycles. Therefore, rather than deploying replicated prepackaged instances of functionality, with microservices the operator can deploy functionality on demand at the scale required. This approach further enhances the efficiency of resources utilization. It also greatly simplifies deployment of new functionality because the operator can add features/perform upgrades on a set of microservices without impacting adjacent services. Automation. One of the main drivers for the evolution of the core network is the vision to deliver networks that take advantage of automation technologies. Across the wider ICT domain, machine learning, artificial intelligence, and automation are driving greater efficiencies in how systems are built and operated. Within the three GPP domains, automation within Release 15 and Release 16 refer mainly to self-organizing networks, SUN, which provide self-configuration, self-optimization, and self-healing. These three concepts hold the promise of greater reliability for end users and less downtime for service providers. These technologies minimize lifecycle costs of mobile networks through eliminating manual configuration of network elements as well as dynamic optimization and troubleshooting. Operators using SUN for LTE have reported accelerated rollout times, simplified network upgrades, fewer dropped calls, improved call setup success rates, higher end-user throughput, alleviation of congestion during special events, increased subscriber satisfaction and loyalty, and operational efficiencies, such as energy and cost savings and freeing up radio engineers from repetitive manual tasks. SNS Telecom and IT, 2018. 5G holds unique challenges, however, which makes automation of configuration, optimization, and healing a core part of any service provider's network. The drivers for this include the complexity of having multiple radio networks running and connecting to different cores simultaneously, the breadth of infrastructure rollouts required, and the introduction of concepts such as network slicing, dynamic spectrum management, predictive resource allocation and the automation of the deployment of virtualization resources outlined above. In addition, we expect that machine learning and artificial intelligence will become further integrated across all aspects of the mobile systems in the coming years. References a. The 5G Business Potential, Ericsson Report 2017. SNS Telecom and IT. Sun, Self-Organizing Networks, in the 5G Era, 2019-2030 Opportunities, Challenges, Strategies and Forecasts. To view the full reference list for the book, click here. Chapter 11, Network and Service. Architecture Overview. This chapter provides an in-depth discussion on the main design principles in the 5G core architecture. It provides a thorough grounding in the core areas of network slicing, service-based architectures and the decision-making processes behind them. After completing this chapter, readers will be well-versed in all the aspects of the 5G core architecture and understand the fundamental principles that form its basis. It illustrates how roaming, devices, mobility and policies are all managed within the main scenarios for 5GC. Finally, it outlines the main principles of 5G NR and its relationship to the 5GC. 5G, 5G Core, 5G Networks, 5G NR, Architecture, Non-Standalone Architecture, Service-Based Architecture, REST, Policy Control, Mobility, Voice, EPS Fallback, Messaging, Devices, Public Warning. Network slicing. Introduction. Balancing evolution and disruption. Work on designing and specifying a core network for 5G was done in parallel with and in close cooperation with the teams designing the 5G radio network. One key principle with the design of the 3GPP 5G core architecture was not providing backwards compatibility for the previous generations of radio access networks, GSM, WCDMA and LTE. Previously, when new access network generations were developed, each one had a different functional split between the core network and the radio network, as well as new protocols for how to connect the radio and core networks. For example, when GPRS Packet Data Services for GSM, 2G, was designed back in the mid-90s, it included a frame relay-based interface, GB, between radio and core. WCDMA, 3G, designed a couple of years later, came with an ATM-influenced interface, IU, for connecting radio and core. Finally, when LTE, 4G, was designed around 2007-2008, it brought the new IP-based S1 interface for connecting radio and core networks. In addition, the different methods for addressing battery savings and scheduling on devices meant that each new generation came with similar but still slightly different functionality and used different data communication protocols for the networking layer. Over time, this has created complexity in network architecture, as most service providers have deployed a combination of 2G, 3G, and 4G on different frequency bands to provide as good coverage and capacity as possible for a heterogeneous fleet of devices. The 5G core, however, brought a mindset shift aiming to define an access-independent interface to be used with any relevant access technology as well as technologies not specified by 3GPP such as fixed access. It is also, therefore, intended to be as future-proof as possible. The 5G core architecture does not include support for interfaces or protocols towards legacy radio access networks, S1 for LTE, IUPS for WCDMA and GB for GSM/GPRS. It instead comes with a new set of interfaces defined for the interaction between radio networks and the core network. These interfaces are referred to as N2 and N3 for the signaling and user data parts respectively. The N2/N3 protocols are based on the S1 protocols defined by 3GPP for 4G LTE, S1AP and GTPU, but efforts have been made to generalize them in the 5G system with the intention to make them as generic and future-proof as possible. N2/N3 are described in section. While GSM and WCDMA access technologies were not discussed much during the 3GPP work to define the 5G core architecture, LTE was. This is because LTE is the most important mobile radio access technology globally and will likely remain so for a long time. Because of this, efforts were made to define how to connect LTE access to the new 5G architecture. Backwards compatibility for devices and LTE radio access was not addressed, but the LTE specifications were complemented to make it a second access technology supporting the same architecture and the same N2/N3 interfaces, protocols as NR. Essentially, this means that any access network that supports N2/N3 could be connected to the new 5G core architecture. In the context of the new architecture, 3GPP has so far specified such support for LTE, NR, and combinations of LTE and NR. 3GPP architecture options. The outcome of the 3GPP work on the 5G network architecture was a number of architecture options, based on 3GPP making three important decisions. To specify LTE support for the new 5G architecture, to specify support for combinations of LTE and NR access, to specify an alternative 5G architecture based on an evolution of LTE/EPC. We will discuss each of these below. The key document for the technical study on the 5G network architecture in 3GPP is the Technical Report 3GPP-TR. The fact that LTE access support is specified for the new 5G architecture means that an LTE access network in practice has two ways of connecting with a core network, potentially simultaneously and selected on a per-device basis. Using S1 connectivity to an EPC core network using N2/N3 to a 5GC core network. Note that it is not only the network interface and associated logic that needs to change when migrating from S1 to N2/N3, but connecting LTE to 5G core also requires a new quality of service concept that impacts the radio scheduler. While this is within the scope of 3GPP specifications in Release 15, it remains to be seen if any LTE networks will actually be converted to connect to the 5GC core network, or if service providers will instead rely on maintaining the S1 connection to EPC combined with interworking between EPC and 5GC, a solution we will describe further in section. When defining the 5G radio access network specifications, two variants of combining LTE and the new 5G radio access technology, NR, were discussed. Each one relies on the assumption that one of the technologies will have a larger geographical coverage and therefore be used for all signaling between devices and the network, while the other radio technology would be used to boost user traffic capacity inside geographical areas where both access technologies are present. The non-standalone NSA architecture, in conjunction with extending the new 5G architecture to not only include NR access but also LTE access, a parallel track was started in the 3GPP Release 15 work. This was driven by a widely established view in the telecom industry that there was a need for a more rapid and less disruptive way to launch early 5G services. Instead of relying on a new 5G architecture for radio and core networks, therefore, a solution was developed that maximizes the reuse of the 4G architecture. In practice, it relies on LTE radio access for all signaling between the devices and the network, and on an EPC network enhanced with a few selected features to support 5G. The NR radio access is only used for user data transmission, and only when the device is in coverage. See Fig. The non-standalone architecture. One drawback with this architecture is that NR can only be deployed where there is already LTE coverage. This is reflected in the name of the solution, the NR non-standalone (NSA) architecture. Another drawback is that the available network features are limited to what is supported by LTE/EPC. The main differences in terms of capabilities are in the areas of network slicing, quality of service handling, edge computing flexibility, and overall core network extensibility/flexibility for integrating towards applications in an IT-like environment. These will be discussed in subsequent chapters. In summary, there are 4 ways that LTE and/or NR can be deployed. Only LTE for all signaling and data traffic, only NR for all signaling and data traffic, a combination of LTE and NR where LTE has the larger coverage and is used for signaling while both LTE and NR are used for data traffic, a combination of LTE and NR where NR has the larger coverage and is used for signaling while both LTE and NR are used for data traffic. Add 2 possible core networks EPC and 5GC, and you therefore get 4 2 is equal to 8 possible network architectures. In order to create a common terminology around different variants of deploying radio access technologies, the concept of options 1.8 was proposed during the initial technical work with the 5G architecture, 3GPP SP 160455. 2016. These are illustrated in Fig. The possible combinations of 5G radio and core networks. It was decided at an early stage that options 6 and 8 should not be progressed further as they assumed connecting NR access directly to EPC, something that would impose too many limitations on NR in order to provide for backwards compatible with EPC functionality. Since option 1 referred to the existing 4G architecture, this meant that the technical work proceeded on options 2, 3, 4, 5, and 7. Out of these, priority in the specification work was given to the 2 variants that were assumed to have the largest market value, option 3 and option 2. Irrespective of the decisions to limit the number of options, this is an area where it may be argued that 3GPP has created too much flexibility for its own good, as so many variants may increase cost and complexity across the industry ecosystem for radio networks and devices. The full impact of this remains to be seen. From a 5G core network perspective, the 4 combinations of radio access technologies, options 2, 4, 5, and 7, all use more or less the same interface, protocols, and logic. This is the first attempt to create an access-independent interface between the core network and whatever access technology that is used. Option 3 is the popular name for non-standalone, or NSA, architecture described above. It was the first 5G network architecture to enter commercial services as it allows for expanding from the existing 4G LTE/EPC architecture, facilitating a smooth introduction of 5G, even if it is mainly addressing existing mobile broadband services. The formal name of the NSA radio network solution is ENDC, short for EUTRAN NR Dual Connectivity. We describe the key EPC features to support 5G NSA in Chapter 4, and the new radio architecture concept in Chapter 12. We then dedicate the rest of this book to the new technologies and concepts defined for the 5G core architecture as defined in 3GPP Release 15. The 2 key reference documents for this are the 3GPP specifications 3GPP-TS and 3GPP-TS. The rest of this chapter provides readers with a high-level description of the 5G core architecture and introduces the key components and functionality. In subsequent sections, we describe the details and logic of each network function as well as the protocols specified for different parts of the network architecture. We start off describing the most fundamental aspects of 5G Core and the most important features and sections. In addition to this, there are more capabilities defined that can optionally be used to support more advanced use cases. These are described in sections. Concluding this chapter is a brief overview of the 5G radio technology and network architecture in section. A final note: in this chapter we refer to the mobile device connecting to the network simply as a device, while in subsequent chapters this is often referred to as a UE, the abbreviation for the 3GPP term user equipment. The same goes for the radio base station that is later referred to using the 3GPP term GNB for NR. Two perspectives on 5G Core when comparing to the existing EPC architecture. The 5GC architecture is simultaneously very similar and very different. The user data processing parts, as well as the integration with 3GPP radio access networks, are quite similar between the new 5GC and the traditional EPC network architecture, originally defined for 4G per LTE. The part of the network that contains signaling-only functionality is on the other hand very different. Another difference between the EPC architecture used for 4G and 5G NSA is that the architecture of 5G Core can be visualized and described in two different ways. The first visualization shows the way different network functions are connected. The major difference compared to previous 3GPP architectures in this visualization is the concept of service-based interfaces. It means that the network functions that include logic and functionality for processing of signaling flows are not interconnected through point-to-point interfaces but instead exposing and making available services to the other network functions. For each interaction between network functions, one of these acts as a service consumer, and the other as a service producer. We will describe this concept in more detail in section. This representation of the architecture is shown in Fig. 5G Core architecture visualized with service-based interfaces. At a first glance, this architecture may look quite complex to the reader, and we will therefore describe the functionality and key features of the different parts of the architecture step by step below. Firstly, however, let's look at the other visualization of the architecture that illustrates how network functions interact with other network functions, represented by traditional point-to-point interfaces. Showing these interfaces can be useful to illustrate which of the network functions that utilize, or consume, the services of which other network functions. Even if all the network functions in theory could be connected in a full connectivity mesh, the actual call flows define which service combinations that apply in real operations. And these combinations are visualized as logical interfaces, or more correctly reference points, in the view shown in Fig. That is the main value of the point-to-point representation. The 5G Core architecture visualized with point-to-point interfaces. Another difference between the two ways of representing the architecture, apart from illustrating how different network functions interconnect, is that some network functions are only applicable in one of the representations. In the service-based representation in Fig, the two network functions NRF and UDSF are visible, highlighted in black. They are described below, but for now it can be noted that they are only applicable to the service-based representation of the architecture view. UDSF has a point-to-point interface name assigned, N18, but it is less useful to illustrate as it can connect to any other network function. For more details on UDSF. Service-based architecture, SBA. The concept of service is a major difference in 5G Core compared to previous generations of traditional network architectures represented by nodes or network elements connected by interfaces, is the usage of service-based interactions between network functions. This means that each network function offers one or more services to other network functions in the network. In the 5GC architecture, these services are made available over network function interfaces connected to the Common Service-Based Architecture (SBA). In practice, this means that functionality supported in a specific network function is made available and accessible over an API, Application Programming Interface. It shall be noted that this architecture applies to signaling functionality only, not to the transfer of user data. HTTP REST interfaces. The communication method defined for 5G Core relies on the widely used HTTP REST paradigm that are a set of rules or guidelines that define how web communication technologies access services from distributed applications using APIs. REST is short for Representational State Transfer and defines a set of design rules for how to implement the communication between different software modules in a networked architecture. This is the standard way of designing IT networking applications today, and it has been selected by 3GPP as a means of allowing for tighter integration between the mobile networks and surrounding IT systems, as well as for allowing for shorter and simplified service development efforts. The expectation is that the network capabilities shall be easier to extend when using the relatively lightweight Service-Based Interface (SBI) concept than if using a more traditional point-to-point architecture that relies on detailed and extensive protocol specification efforts. Using SBI and APIs can also be seen as a logical choice by 3GPP when specifying the 5G Core network, as the 5GC software applications that implement the network functions are assumed to be executing in an IT-like or even shared IT environment, typically in a cloud data center. A harmonization of both software technologies and IT architecture across the mobile network solution and supporting IT applications is to some extent possible with this approach. Fig shows 3GPP network functions utilizing HTTP REST for service-based communication. They are logically interconnected to a common networking infrastructure. Network functions utilizing service-based interfaces. HTTP REST uses message syntax from the widely used HTTP web protocol, and relies on the concept of resource modeling, which means that a distributed software application can be addressed through Uniform Resource Identifiers, URIs, in practice a web address pointing at a resource or set of resources. On top of this, a very simple set of commands, standard HTTP methods, are being used. The most important ones are listed below. Get this is used to fetch data from a server. It shall not change any data. Post this is used to send data to a server. Put this is also used to send data to a server, but it replaces existing data. Delete this is used to remove data from a server. An important aspect of REST is that all communication must include the full set of information needed for a specific processing action. It must not rely on previous messages, and hence it can be considered as stateless. Utilizing this principle for software design allows for excellent scalability and distribution capabilities for the system. More details on the HTTP protocol are available in Chapter 13. Service registration and discovery. When two network functions communicate over the 3GPP SBA architecture, they take on two different roles. The network function that sends the request has the role of a service consumer, while the network function that offers a service and triggers some action based on the request has the role of a service producer. Upon completion of the requested action, the service producer responds back to the service consumer. So far so good, but a critical part of this concept is the mechanism for how the service consumer can locate and contact a service producer that can provide the requested service. The solution is based on the concept of service discovery. Service discovery relies on that a well-known function in the network keeps track of all available service producers and what services they offer. This is achieved through that each service producer, for example a 3GPP network function like the PCF, registers that its services are available. In the 5GC architecture, this registration is done to a dedicated network function that is called the Network Repository Function, NRF. This concept allows the NRF to keep track of all available services of all network functions in the network. It also means that each individual network function needs to be provisioned or configured with the address of one or more NRFs, but it does not need, and shall not have, addresses to all other network functions configured. Let's look at a practical example involving three actual network functions: PCF, AMF, and NRF. The detailed roles and key functionality of AMF and PCF will be more extensively explained below, so for now, just assume they are any network functions that need to interact as part of a specific call flow. It starts with PCF doing a service registration. During the actual registration, the PCF acts as a service consumer, and the NRF as a service producer, basically offering the service of network resource registration to the PCF. Fig illustrates the initial part of the call flow. The PCF registers with the NRF using an HTTP PUT message that includes information about the PCF such as available services, network address, and identity. The NRF verifies that the request is valid, stores the data associated with the PCF registration, and acknowledges the PCF registration with a response back to the PCF. Now the PCF services are available to other network functions through querying the NRF. First part of the call flow: service registration. In the next phase, another network function like the AMF wants to utilize the services of a PCF. This is achieved through first querying the NRF for a list of PCFs offering these services. This phase is called the service discovery. In this case, the AMF is the service consumer and the NRF is the service producer. See Fig. Second part of the call flow: service discovery. The AMF sends a query to the NRF, stating what sort of network function it is asking for, and what services this NF shall support to be of interest. This is done using an HTTP GET message. The NRF filters out all network functions that are registered and are providing the requested services, and then responds back to the AMF. When this step is finalized, the AMF can make a selection of a PCF that fulfills the service requirements, and then contact the selected PCF with a service request. In this step, the AMF is again the service consumer, while the PCF is the service producer. This is done using an HTTP POST message. Note that the service request referred to here is not be mixed up with the service request a mobile device sends to the network when it is to move from idle to connected mode. Upon reception of this service request, the PCF determines the applicable policy that is requested by the AMF and responds back to with an HTTP response, Fig. Third part of the call flow: service request. The call flow including all three steps is shown in Fig. Consolidated call flow. Note that these three parts do not usually happen in direct sequence. A network function typically registers with the NRF when it is put into service, while the service discovery and service requests may, for example, take place when a device connects to the network. The rest of the call flow and the subsequent interaction between the network functions is beyond the scope of this chapter, but the concept remains the same through each step, and for all other call flows between network functions interacting with HTTP within the service-based architecture. One network function acts as the service producer, another one as the service consumer. And all communication is done using the HTTP protocol. There is another way of interaction between a service producer and one or many service consumers. This is based on the fact that one or several network functions can subscribe to a service from another network function. The network function acting as service producer then sends notifications to all the service consumers when some specific criteria are met, for example when certain information has been changed. The concept of subscribe and notify removes the need for service consumers to frequently request information from the service producer, instead allowing them to wait for the service producer to notify when something has happened. The core of the core. Having described the new mechanisms for how different network functions communicate, let's now return to the functional view of the network. The core functionality of the network architecture includes functionality for establishing sessions in a secure way and to forward user data to and from mobile devices, providing data connectivity. This is the part of the network that cannot be excluded from any 5G core deployment. In addition to radio network and the NRF described in section, it includes the following 6 network functions. Chapter 12, Other. Fig illustrates the core components of any 5G network. Mandatory components of a 5G network architecture. The AMF is the Access and Mobility Management function. It interacts with the radio network and the devices through signaling over the N2 and N1 interfaces respectively. Connections towards all other network functions are managed via service-based interfaces. The AMF is involved in most of the signaling call flows in a 5G network. It supports encrypted signaling connections towards devices, allowing these to register, be authenticated, and move between different radio cells in the network. The AMF also supports reaching and activating devices that are in idle mode. One difference to the EPC architecture is that the AMF, as opposed to the MME, does not handle session management. Instead, the AMF forwards all session management-related signaling messages between the devices and the SMF network function. Another difference is that the AMF, as opposed to the MME, does not perform device authentication itself. Instead, the AMF orders this as a service from the AUSF network function. The AMF functionality is described in more detail in Chapter 7. The SMF is the session management function, meaning as the name suggests that the SMF manages the end user, or actually device, sessions. This includes establishment, modification and release of individual sessions, and allocation of IP addresses per session. The SMF indirectly communicates with the end-user devices through that the AMF forwards session-related messages between the devices and the SMFs. The SMF interacts with other network functions through producing and consuming services over its service-based interface, but also selects and controls the different UPF network functions in the network over the N4 network interface. This control includes configuration of the traffic steering and traffic enforcement in the UPF for individual sessions. In addition to this, the SMF has a key role for all charging-related functionality in the network. It collects its own charging data and controls the charging functionality in the UPF. The SMF supports both offline and online charging functionality. Furthermore, the SMF interacts with the PCF network function for policy control of user sessions. The SMF functionality is described in more detail in Chapter 6. The user plane function, UPF, has as the main task to process and forward user data. The functionality of the UPF is controlled from the SMF. It connects with external IP networks and acts as a stable IP anchor point for the devices towards external networks, hiding the mobility. This means that IP packets with a destination address belonging to a specific device is always routable from the Internet to the specific UPF that is serving this device even as the device is moving around in the network. The UPF performs various types of processing of the forwarded data. It generates traffic usage reports to the SMF, which the SMF then includes in charging reports to other network functions. The UPF can also apply packet inspection, analyzing the content of the user data packets for usage either as input to policy decisions, or as basis for the traffic usage reporting. It also executes on various network or user policies, for example enforcing gating, redirection of traffic, or applying different data rate limitations. When a device is in idle state and not immediately reachable from the network, any traffic sent towards this device is buffered by the UPF, which triggers a page from the network to force the device to go back to connected state and receive its data. The UPF can also apply quality of service (QoS) marking of packets towards the radio network or towards external networks. This can be used by the transport network to handle each packet with the right priority in case of congestion in the network. The UPF functionality is described in more detail in Chapter 6. The UDM is the Unified Data Management function. It acts as a front end for the user subscription data stored in the UDR, more on that further down, and executes several functions on request from the AMF. The UDM generates the authentication data used to authenticate attaching devices. It also authorizes access for specific users based on subscription data. This could, for example, mean applying different access rules for roaming subscribers and home subscribers. In case there are more than one instance of AMF and SMF in the network, the UDM keeps track of which instance that is serving a specific device. The UDR, the Unified Data Repository, is the database where various types of data is stored. Important data is of course the subscription data defining various types of network or user policies. Usage of UDR to store and access data is offered as services to other network functions, specifically UDM, PCF, and NEF. The functionality of the Authentication Server function, AUSF, is quite limited but very important. It provides the service of authenticating a specific device, in that process utilizing the authentication credentials created by the UDM. In addition, the AUSF provides services for generating cryptographical material to allow for secure updates of roaming information and other parameters in the device. Connecting the core network to mobile devices and radio networks. The description above outlines the key parts of the core network architecture. The connections to the radio network and the devices are shown in Fig. Connecting 5G RAN and 5G core. N2 is a key reference point in the 5G network architecture. All signaling between the radio networks and the core network, fronted by the AMF, is carried across this reference point. It should be noted that there is a naming inconsistency in the 3GPP set of Release 15 specifications here, as the specifications developed by the RAN working groups use the term NGC interface while the architecture and core teams use the term N2 reference point in their specifications. In this book we consistently use N2. The signaling carried across N2 is based on the NGAP protocol. There are multiple types of signaling procedures supported over N2. Procedures supporting management of N2 such as configuration of the interface itself. 1GNB, the 5G radio base station, can be connected to multiple AMFs for load sharing, resiliency, and network slicing purposes. Procedures related to signaling for a specific UE/device. Each UE/device is always only associated with a single AMF, except for some special cases related to simultaneous roaming in 3GPP and non-3GPP networks. This signaling can be divided into three different types of procedures: signaling related to forwarding of messages between the device and the core network, This is based on the NAS protocol, short for Non-Access Stratum. In the 5GC architecture, individual NAS messages are either managed by the AMF or the SMF. The SMF manages NAS messages related to session management, and in that case, messages are passed between SMF and device with the help of the AMF, as there is no direct connection between the SMF and the radio network. The AMF manages all other NAS messages without involving the SMF. It shall be noted that NAS can also be used to transparently carry some messages to and from other network functions. This is described in more detail in Chapter 14. Signaling related to modification of the stored data for a specific device. The UE context signaling related to management of events like handovers between radio cells or access networks and paging of devices that are in idle mode. One difference to the EPC architecture is that for 5GC, also the reference point between the device and the core network, the AMF, has its own name. This is called N1, over which the NAS messages described above are carried. It means in practice that the NAS messages are carried transparently over the air interface UU and the RAN core interface N2. But from a logical perspective, N1 is shown as its own reference point in the architecture. The NAS messages that relate to the AMF functionality are of course managed by the AMF, while the NAS messages that relate to SMF functionality are forwarded by the AMF to the applicable SMF over the logical N11 interface. After that, the AMF has performed basic NAS message processing for e.g. security. In practice, N11 is realized through utilizing the services available over the NAMF and NSMF interfaces in the service-based architecture. It should be noted that one device is always served by one single AMF, but the same device can be utilizing data sessions managed by more than one SMF. This gives additional flexibility compared to the EPC architecture, and for example allows for simultaneous connections to multiple logical networks with different treatment, policies, and rules being applied for the routing of user data. Note again, as mentioned above, there is actually a case when the device is simultaneously served by two AMFs, but that is a very specific case related to non-3GPP access, and is out of scope for this chapter. Fig shows the case when one device is served by a single AMF but have sessions established with two SMFs, each with its own UPF. This concept is further described in section in the context of network slicing. Multiple service connections with individual SMFs and UPFs. Mobility and data connectivity as described above. User data is handled in the UPF, the user plane function, in the core network. Data is transported between the radio access network and the UPF over the N3 reference point. Data is tunneled across N3, meaning that IP routing is done on the tunnel header IP address instead of the end-user IP address. This allows for maintaining a stable IP anchor point even though the device is moving in the network. It also allows the same mechanisms and transport routing to be used independently of the type of data that is carried. Besides IP packets, the 5G architecture specifications also include support for Ethernet frames and so-called unstructured data. The concept is very similar to how it is done in the EPC architecture, where the corresponding interface or reference point is called S1U. N3 includes a new way of managing the quality of service of specific data flows and how to map data flows to tunnels. On the other side, the UPF connects to external data networks. Here IP packets are in general routed based on the actual IP address of the device, meaning that the traffic is not tunneled. The reference point is called N6 and corresponds to SGI in the EPC architecture. For Ethernet sessions, N6 is a layer 2 link instead of a routable IP network. There are also possibilities to tunnel end-user data over N6 using virtual private networking, creating secure tunnels, for example for enterprise connections. FIG shows the interfaces related to user data processing and transport in the 5G architecture. The user plane connection to radio networks and external data networks. The SMF controls the behavior of the UPF. This is done through signaling over the N4 reference point. As described above, there could be several SMF/UPF pairs simultaneously managing traffic for one and the same device. The control of the UPF is done per end-user data session, where the SMF can create, update, and remove session information in the UPF. In addition, some functions are defined also for individual data flows. Some of the key features in the SMF related to UPF control include controlling traffic detection rules to be used in the UPF, controlling packet forwarding rules to be used in the UPF, controlling usage reporting rules to support policy and charging functionality in SMF. The UPF then reports usage based on these rules towards the SMF. Reporting can be done both for the total traffic associated with a data session, as well as for individual traffic flows, providing quality of service parameter values to the UPF for QoS enforcement of data flows. For example, limitations of the available data rate. The 5G core architecture includes more extensive support and flexibility for different levels of data mobility compared to the EPC architecture specified for 4G and inherited for use with 5G NSA. One fundamental concept is the 3 session and service continuity modes, abbreviated to SSC modes 1, 2, and 3. They indicate different ways of dealing with existing data sessions when the device moves across the network. This allows for a more flexible selection between prioritizing a stable mobility anchor point or prioritizing low user data delays. The SSC modes require corresponding support from the device, otherwise they will not work. FIG is an overview of the 3 SSC modes. Session and Service Continuity Modes 1, 2, and 3. SSC Mode 1 means that the IP address is maintained regardless of movements in the network. The same IP anchor point, UPF, is accessible and can be used across the network. SSC Mode 2 means the opposite of SSC Mode 1. The network will release and trigger the device to re-establish new sessions as the device moves around in the network. The network decides to release the session based on operator policies, for example based on a request from an application function in the network. When the device requests a new session, the network can select a new UPF which is more suitable to the service, for example a UPF that is located closer to where the device is currently located. As opposed to SSC Mode 1, SSC Mode 2 means a short interruption of the service, which may or may not be acceptable depending on what end-user service that is being targeted. SSC Mode 3 is a bit more advanced, as it tries to combine some benefits of both options 1 and 2. It allows for the same low delays as SSC Mode 2 through triggering release and re-establishment of IP sessions using new UPFs, but allows for a continuous service availability as with SSC Mode 1, albeit likely with a delay that may not fully meet the needs during the mobility phase. This is done through first establishing the new session and connection to the new UPF before releasing the session and connection anchored in the old UPF. This puts additional requirements on the device as it needs to maintain 2 sessions and 2 IP addresses for the same service for a limited time. The selection of a suitable SSC mode is preferably be done based on needs of the service itself. One example is if a service requires very low network delays while being implemented in a network covering a large geographical area. A large coverage area means that the IP anchor point for SSC Mode 1 would need to be centralized to a location where all radio network base stations can be reached, and preferably with a not too long and decently uniform delay. But having the IP anchor point, the UPF, in this location may not meet the delay requirements, which instead calls for IP anchor points closer to the access, to reduce the delay coming from the transport networks connecting different cities or even different parts of the country. So, the SSC mode may second in this case be needed to meet the delay requirements, with the drawback that the IP address and the location of the IP anchor point and the application server where the service is executing needs to be changed as the device moves in the network. The selection of SSC mode for a session is done by the SMF, based on a combination of allowed SSC modes in the subscription data, and the request from the device. The SSC mode does not change once a session is established. One limitation that should be noted is that while SSC modes 1 and 2 can be used for both IP and Ethernet type sessions, SSC mode 3 only works for IP. Somewhat related to the ability to access local services using SSC mode 2 or 3, the concept of Local Area Data Network, abbreviated LADN, supports restricting access to certain services to only be possible in certain geographical areas, defined as several tracking areas. From a simplistic perspective, a tracking area can be viewed as a collection of radio cells that combined together cover a larger geographical area. A mobile network normally contains many tracking areas that each contain many cells. Using the LADN mechanisms, the operator can define some services to be available only in certain geographical areas. For a device to access such a service, the subscription used for the device need to include the corresponding LADN service support. Further details on SSC modes and LADN are available in Chapter 6. A special feature of the 5G Core UPF is that two UPFs can be deployed in series, then connected via an interface referred to as N9. There are three main use cases for this. 1. Network-wide mobility. 2. Breakout of selected data flows. 3. Roaming with home routing. We cover the first two cases below. The third case will be described in section. To provide full mobility with a stable IP anchor across the full network, there may be a need to connect two UPFs. If this is required or not depends on the operator network configuration, specifically how the transport network between the base stations in the radio network and the various core network sites has been designed. An example is shown in Fig. Assume a device attaches over a radio cell in the left-hand NR coverage area. The UPF1 will be selected and be serving as the IP anchor for the device, connecting to the Internet or another data network that offers some end-user services, e. IP mobility when interconnecting two UPFs. The device then moves to another part of the network, where the radio base stations cannot connect to UPF1 due to limitations in the transport network configuration. The SMF then allocates UPF2 to serve as a termination point for the new N3 interface and connect back to UPF1. Through this method, there is no change to the IP address of the device or the point of interconnect. The second case is a new concept in 5GC compared to EPC, the ability to apply classification and traffic management in the UPF to selectively send IP packets to different IP interfaces. The typical use case for this scenario is to allow for some traffic to be terminated at or close to the edge of the network, for example, to secure the lowest possible data plane latency, or to protect sensitive data from being intercepted in the more centralized parts of the network. The architecture therefore involves two UPFs again, connected in series. See Fig. Breakout of selected data flows using uplink classifier. This concept relies on a new mechanism in the UPF called the uplink classifier, ULCL, that filters out IP packets coming uplink from the device and that match certain classification criteria, and sends these packets to a separate IP interface connected to a local network. This interface happens to also be called N6. For this to work, the ULCL function must be applied in the UPF closest to the access network. Packets that do not meet the selection criteria are sent to the centralized UPF over the N9 interface. In the downlink, data flowing towards the device from both the centralized UPF and the local UPF is combined into one single data stream in the UPF closest to the access network. The ULCL function is controlled by network rules provided by the SMF that manages the specific IP session. The SMF decides based on policies to either include or not include an ULCL function and an extra UPF in the data path for a given IP session. Signaling for ULCL is handled over the N4 reference point between SMF and UPFs. This functionality is completely transparent to the devices, and the devices are therefore not aware of if ULCL and local breakout of traffic is applied in the network or not. There is also another solution for providing breakout of selected data flows. This relies on IPv6 being used with multi-homing. More information on both ULCL and IPv6 multi-homing is provided in Chapter 6. Policy control and charging. The 5GC architecture includes extensive functionality for policy-based control of traffic and user services. This functionality is similar to what is supported in the 3GPP EPC architecture but includes additional new functionality that we describe below. Policies can be viewed as rules for how users and data sessions and data flows shall be controlled or managed, including what services are allowed or disallowed, how charging shall be done, what quality of service that applies, etc. Policies can be applied with different levels of granularity, e. Policy rules that apply to all users in the network, policy rules that apply to all services for a specific user, policy rules that apply to specific data sessions or data flows for a given user. A centerpiece of the 5GC policy control architecture is naturally the policy control function, PCF, which interacts with several other network functions as shown in Fig. It should be noted that we have not as yet introduced some of these network functions in this book. These are therefore illustrated in black and are further described in later chapters. PCF connections to other network functions. The main document describing the 5G policy architecture is the 3GPP technical specification. On a high level, the functionality of the PCF belongs to one of two main areas: policy control related to data sessions, policy control not related to data sessions. Policy control not related to data sessions refers to how service providers can control the way a specific. That is the heart of 5G core networks. If it helped, a quick subscribe keeps more summaries coming. So how do network and service connect? That is exactly where we started. Go back to the top and watch it click into place.